Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about putting this problem to rest? Smoke is coming out of my ears trying to solve this problem, you say. Worry not, my friends. I'll walk you through this problem like there's no tomorrow. No one will be like, make this stuff make sense by the end of this video. Oh no. On my watch? Heck no. Or maybe you've actually solved the problem and want to confirm your solution. Or maybe you haven't even attempted to solve the problem, but you want to just chill out and look at the solution regardless. In either case, let's get this show on the road, shall we? Oh yes. So the problem is asking us how quickly a group of 4 people, namely yours truly, Jacob, George, Beth, and Stella, can cross a bridge with a flashlight. So, for example, if George and Beth cross the bridge together while one of them holds the flashlight, since George can cross the bridge in 8 minutes and Beth can cross the bridge in 10 minutes, and both of them together can cross the bridge in 10 minutes. So George has to slow down and match Beth's pace, since Beth is the slowest of the two. Makes sense? And once they get to the other side and one of them comes back, let's say George, he returns to the initial position in 8 minutes with the flashlight. And then Jacob and Stella can cross the bridge, one of them holding the flashlight, in 12 minutes, and so on and so forth. So in order to solve this infamous problem, we'll be utilizing an area of mathematics, a subgenre of combinatorics called graph theory. We're bringing out the big guns today, my friends. We're not fooling around with this one. Oh no. So we'll be modeling our physical situation here with a graph. What is a graph, you ask? Good question. When I say graph, I don't mean an XY Cartesian graph of a function. The graphs in graph theory are something else entirely. So a graph basically is an abstract model of a network. A network can be anything: a road network, a telephone network, relationships between people, etc. So now let's give the strict mathematical definition of a graph. Let's first look at a simple graph. Points A, B, and C are called the vertices of a graph. The lines between these points are called the edges of the graph. So the vertices of a graph are the objects being studied, whether a person, a town, etc. And the edges are the connections between the vertices, the relationships. So the edge AB, for example, in our simple graph here, belongs to the graph. Since E belongs to the graph, and A and B are called the end vertices of E, we say that E is incident with A and B, and that A and B are adjacent since there's an edge connecting them. And this is the notation we use here to say that A and B are adjacent. Oh yes. So now we're ready to define mathematically what a graph is. A graph consists of 2 sets: V, the set of all vertices of the graph, and E, the set of all edges of the graph, which are unordered pairs from V. And you see here E is the subset of all unordered pairs U1, U2, such that U1 and U2 belong to V. So now let's define what a weighted graph is. A weighted graph is a graph where each edge of the graph is assigned a number, as you see in this example here. So now that we define what a graph is, what a weighted graph is, now we're ready to present a powerful tool with which we'll be taming our problem at hand. This tool ensures us that we'll always be able to obtain the shortest weighted path from any vertex to any other vertex of a graph. So without further ado, live and in living color, the often imitated but never duplicated, making its debut on this channel, the one and only Dijkstra's algorithm. Oh yes. Dijkstra's algorithm is a process that will ensure that we find the shortest weighted path between any 2 vertices of a graph. So we'll be using this simple weighted graph to explain how Dijkstra's algorithm works. So Dijkstra's algorithm is as follows. Suppose we want to calculate the shortest distance between vertex or node A and every other node of this graph. We just have to keep track of some information while iterating through this algorithm. First things first, we need to keep track of which nodes we haven't visited yet. So in the first step, we mark all nodes as unvisited. We create two lists, the list of visited nodes, which is empty for the time being, and the list of unvisited nodes, which contains all the nodes of the graph, since we haven't started yet. Now we make a table. We assign to all nodes a tentative distance value that will be changed over time. As you see here in this table, we have 3 columns. In the first column, we have the nodes. In the second column, we have the shortest current distance from node A to the node in question. So in the beginning of this algorithm, we don't know anything about any distances to any other node from node A. So we set A to 0, since the distance from A to A is 0, of course. And every other distance we set to infinity for the time being. And in the last column, we store the previous node that leads us to the current shortest distance. And this column will be empty in the beginning because currently we have no information about this. Make sense so far, my friends? Now we can start with the first iteration. Since we start at node A, we start by calculating the distance to all unvisited neighbors of A. All the vertices that are adjacent to A that are unvisited. In other words, the distance from A to B is 2, and the distance from A to D is 8. And now we can update our table if we have found a new shortest distance to one of the unvisited nodes. So B and D are unvisited, and the current shortest distance is infinity, so we can update the distance from A to B to 2, and store A as the previous node in our table. And the same applies to the vertex D, or node. We update the distance to 8 and store A as the previous node. Now our iteration ends here. Now we mark A as a visited node, remove it from the unvisited nodes list, and place it in the visited nodes list. Now we pick a new current node to explore this graph further. We always choose the node with the current minimal distance in all our unvisited nodes. So looking at our table, A has a distance of 0, but A is already visited. We have B, an unvisited node, with a distance of 2. And we have D with a distance of 8, and all the other nodes have infinite distances. So B has the current shortest distance of all unvisited nodes. So B becomes our new current node. Now we calculate the distance to all unvisited neighbors of B, like we did with the first step. So the unvisited neighbors of B are E and D, and the distance calculation is as follows. Since B has a current distance of 2, we need to add this to the weight of the edges to E and D, as you see here. So let's first look at node E. Node E will have the current distance 8 from A through B. Now we need to check if 8 is less than the current shortest distance that we stored in our table. The current shortest distance we stored in our table is infinity, and 8 is certainly less than infinity the last time I checked. So we update our shortest distance to E to 8 and set B as our previous node. Now let's look at the node D. D will now have a distance of 7, 2 plus 5 equals 7, from A through B. So we compare this 7 to our current value, 8, which is stored in our table. And since 7 is less than 8, we set the current value of the shortest distance to 7. We set the previous node to B. Now we're finished with B, since we examined all unvisited neighbors of B, and we set B as visited. The next step, we choose a new current node from all unvisited nodes, just like we did before, and we choose the node with the minimal distance. The node with a minimal distance, in this case, is D. Since it has a distance of 7, we now calculate the distance to all unvisited neighbors of D, and we need to add 7 to these distances. So let's start with E. The distance from A to E through D is 10, 7 plus 3, but 10 is greater than our current distance 8 that we stored in our table, so we'll leave it as it is. We don't update. So now looking at F, the current distance we have in our table is infinity, but now we get a distance of 9 from A to F through D. So we update our shortest distance in the row F, set it to 9, and set the previous node to D. Now we mark D as visited, and we choose a new current node from the unvisited nodes list with the current minimal distance, and this will be E. So we calculate the distance from E to C and E to F, and we add 8 to these distances, of course. Let's start with C. We now have a distance of 17 from A to C through E, and 17 is certainly less than infinity, last time I checked. So we update the table, set the shortest distance to 17 and the previous node to E. When we look at F, we have a distance of 9 from A through E, which is exactly the same value we have in our table, so we don't update anything. So we're finished with the node E, mark it as visited, and we have C and F left as unvisited nodes. C has a distance of 17 and F a distance of 9, so we choose F as the new current node, and the only unvisited neighbor is C. And we see we have a distance of 12 from A to C through F, so we update the shortest distance from A to C to 12 and set the previous node to F and mark F as visited. This leaves us with C. Since C has no unvisited neighbors, we mark C as visited as well. So we're finished here, my friends. So we have some important information stored in our table about this graph. We have the shortest distance from A to every other vertex in this graph, and we have the previous node, which helps us reconstruct the shortest path. So for example, if we want to reconstruct the shortest path from A to C, the first thing we see is that the shortest distance is 12. To find the shortest path, we start from the node C, look at the previous node, which is F. We mark this edge from F to C, and we look at F, and we see the previous node is D. So we mark the edge connecting D and F, and when we look at D, the previous node is B, so we mark the edge connecting B and D. And when we look at B, the previous node is A, so we mark the edge connecting A and B. And so we've constructed the shortest path from A to C, my friends, as you see here. Oh yes. Okay, so now that we know what a graph is, what a weighted graph is, and how to use Dijkstra's algorithm to construct the shortest weighted path from any vertex to any other vertex of a graph, now we're ready to represent our physical situation here with a graph. So here's the graph that represents the problem at hand. It's a huge graph, as you see here. That's why I have to scroll through it. Can't just show it in one go. So the vertices of this graph represent the people that are on the other side of the bridge, and the edges of the graph represent the people that are crossing the bridge. So for example, since in the beginning there are no people on the other side of the bridge, then we leave the first vertex without a name. So let's look at our topmost vertex and edge. So I've named the topmost vertex G plus S, since George and Stella are on the other side. So in the first edge, George and Stella are crossing the bridge, and since it takes this duo 12 minutes to cross the bridge, then I've assigned the weight 12 to this edge. The vertex below is named G plus J. That means George and Jacob are on the other side of the bridge. So since it takes George and Jacob 8 minutes to cross the bridge together, and I've assigned the weight 8 to the edge connecting G plus J and the initial vertex. So let's look at this vertex here called S. This means Stella is the only one on the other side. So in the edge connecting S and G plus S, George is the one coming back to the initial position by himself, holding the flashlight. Hence this edge has 8 as its weight, and so on and so forth. I hope you can see the logic of how this graph was constructed and named. Okay, so now, since a lot of different vertices of this graph have the same name, to make things less confusing, we'll assign a number to each vertex. And in total, we have 164 vertices for this graph, as you see here. We're going to make our table and use Dijkstra's algorithm to find the shortest path from vertex 1 to vertex 164. Since vertex 164 is the vertex that represents all 4 of the people on the other side. Okay, so here's our table, my friends, and we're going to go to town on it. Oh yes. So we start with the first iteration. We start from node 1. the unvisited neighbors of 1 are 2, 3, 4, 5, 6, and 7. The distance from 1 to 2 is 12, which is certainly less than infinity. So we update the shortest distance to 12 and set the previous node to 1. And the distance to 3, 4, 5, 6, 7 are 8, 10, 12, 12, and 10. And they are less than infinity again. And we update the shortest distances to these values and set 1 as the previous node. Now we're done with node 1, mark it as visited, and we choose a new current node that is unvisited, that has the minimal distance from 1, which is node 3. So node 3 is our new current node. And so now we calculate the distances to all unvisited neighbors of 3. The distance from 1 to 10 through 3 is 8 plus 8, which is 16. So we update the minimal distance from 1 to 10 to 16, since 16 is less than infinity. And we set the previous node to 3. And the distance from node 11 to 1 is 8 plus 7, which is 15, which is less than infinity. So we update the minimal distance from node 11 to 15 and set the previous node to 3. So we're done with node 3, mark it as visited, and we choose a new current node from our unvisited nodes list, which has a minimum distance to 1. And that node is node 4. So node 4 is our new current node, and we calculate the distances of all unvisited neighbors of 4, which are nodes 12 and 13. The distance of node 12 to node 1 is 10 plus 8, which is 18, and it's less than infinity. So we update the minimal distance from node 1 to node 12 to 18 and set the previous node to 4. The distance of node 13 to 1 is 10 plus 10, 20, and we update the distance to 20, since 20 is less than infinity, and set the previous node to 4. And now we're done with node 4 as well. Mark it as visited, and we choose a new node from the unvisited nodes list, which has a minimum distance to 1. And that node is node 7, which has a minimal distance of 10. And so we continue in this manner, my friends, calculating all the distances of all the unvisited nodes of the current node and updating the table where necessary. One thing to note is that we don't actually have to check all the nodes to find our shortest path. Why do I say this? Because at some point, the shortest distance from node 1 to node 164 becomes 43. And of all the unvisited neighbors of node 164, the ones that have the smallest distance to 1 are nodes 57, 76, 82, 85, 88, 90, 119, and 151. And these nodes have the distance of 35 from node 1. Once you check all these nodes, you're pretty much done, because there are no edges connecting the neighbors of node 164 to node 164 with weights less than 8. And the rest of the unvisited neighbors of 164 have a minimal distance of 36 and above, so you won't be able to update node 164 after that point. Makes sense? So we only need to check 68 nodes pretty much, my friends. And so 43 is the minimal distance from node 1 to node 164. So how do we construct the shortest path? We look at the previous nodes stored in our table. Actually, there are two shortest paths. Let's look at node 82 first. So shortest path number 1 is from node 164 to node 82. to node 28, to node 10, to node 3, to node 1, going backwards. So how do we translate this into a working solution? So as you see here, vertex 3 corresponds to G plus J, which means George and Jacob cross the bridge initially. Vertex 10 corresponds to Jacob on the other side, which means George crosses back. Vertex 28 corresponds to S plus B plus J, which means Beth and Stella cross the bridge. Vertex 82 corresponds to S plus B, which means Jacob crosses back to the initial position, and Jacob and George cross to the other side. And the second solution is similar. The only difference is Jacob is the one that returns after George and Jacob cross the bridge initially. Total 43 minutes, my friends, in both cases. So, the party's over for this problem. Finito la musica. Luis. Wow. Just wow, you guys. Words aren't enough to describe this. What a beast of a problem we just slayed. Combinatorics at its finest. The mystery of this infamous puzzle has been put to rest. I have to say this was an ambitious undertaking by me, my friends. Going into this problem, I didn't know what to expect. Actually, I knew it was going to be hard, but I underestimated the complexity of this problem a bit. So what we have here, my friends, is like a mini dissertation. Luis. Initially, I wanted to have actually 8 people cross the bridge instead of just 4, which is pure lunacy in retrospect, since in that case we'd be dealing with hundreds, if not thousands of vertices instead of just 164. So in that case, you'd need a computer program to solve that problem. And writing programs isn't really my forte, my friends. It's beyond the scope of this channel. The main takeaway of this video is to learn how to use Dijkstra's algorithm by hand. So it took me ages to make this video, not only because of the difficulty of the puzzle, but because I'm working a 9-to-5 job. My work environment is chaotic at the moment. We're in peak season. So besides fighting this puzzle itself, I'm fighting my own fatigue as well, my friends. But I didn't want to put off making this video and make an easier one because this problem was scheduled, I have to adhere to the schedule, whether I like it or not. I'd feel like a failure otherwise if I gave in and made an easier puzzle. So I gritted my teeth, I hunkered down, I grinded, and as a result, we have this beautiful end result to study and to admire and pick apart, my friends. Luis. So that's pretty much it. Comment down below what you think. If you found this difficult, if you solved it another way, shoot a puzzle and category suggestion my way, and I'll see you guys and gals in the next video. Bye-bye.